Hello. Today we start Module 2 from SWAYAM Arpit course under the topic of low energy integrated analog to digital converters. And title of today's module is Low Power Techniques for Capacitive DAC in SAR ADC. Outline of today's lecture is about first power breakdown as a function of sampling frequency. Just as an example to see that how sampling frequency changes the power breakdown. Then one technique which is used for reduction of the area and power and has been known from long time ago. And some of the techniques which are reported now and being followed for reducing the capacitive switching energy in SAR ADC, mainly with respect to DAC, because capacitive DAC switching plays a vital role in the overall energy consumption of the SAR ADCs, which are used for low energy applications. Sampling frequency plays a vital role. Therefore, we need to be concerned and see how sampling frequency can change the contribution of the energy across different factors. So here, two pie charts are shown, which is reported by D. Zhang in 2012. So it is about changing sampling frequency in SAR ADC design in 130 nanometer CMOS technology. One case on the left is the distribution of the contribution of energy consumption for sampling frequency of 1 kilosample per second. So as you notice, DAC switching contributes most, which is 46%, follows by the leakage power, which is 31%. Because sampling frequency is very low, therefore, leakage power is not negligible. Now we will move to higher frequency. For example, here sampling frequency has been increased by a factor 10. So contribution of leakage power drastically reduces and contribution of dynamic power of the logic circuit increases from 20 to 28%. However, contribution of the capacitive DAC is even more, increases from 46% to 64%. Therefore, we are concerned about energy consumption of the capacitive DAC, even in both cases, and that tells us that it is very important to try find the ways to minimize this energy consumption. So one of the techniques, which is relatively an old technique and mainly at the beginning was used to reduce the area of the capacitor array for relatively medium towards high resolution SAR ADC, is to use a split DAC capacitor. But this technique also contributes to reduction of the energy. And therefore, here it is worth to mention the technique. So this technique eventually tries to reduce the sizes of the capacitors. For example, in this example, instead of having the binary weighted capacitors for 6-bit ADC, which goes up to 2 to the power 6 C unit, we divide the array into two parts, capacitive array. One part which is for LSB bits called LSB array, and one part which is for MSB bits called MSB array. Here the division is equal in the sense that 3 bits for LSB array and 3 bits for MSB array. And then the capacitor, which is shown by the value of 8 by 7C, eventually bridges these two arrays together. And because we have two capacitive arrays, therefore we should have two switches for the initialization. The arrangement shown in this slide is mainly with respect to single supply switching. And therefore, comparator also is shown as a single supply comparator. And therefore, the input terminal of the comparator, positive input terminal, needs to be connected to common mode level, not into the ground level or zero level. So similarly, the switching arrangement for the ADC based on the DAC is a little different in the sense that we have two mean and max value of the reference levels, which is V common mode minus V full scale by 2 and V common mode plus V full scale by 2. So I am showing you this scheme because this is not very common in textbooks, and it is good for you to learn about how to manage the reference levels and common mode levels for the case the designs are single supply, because most of the designs these days are single supply. Of course, most of the designs these days are differential as well, but because of the simplicity of the architecture, I am showing you single-ended architecture, but it can be easily extended to a differential architecture. So initialization is happening the same way it happens for the traditional binary weighted capacitive DAC. So therefore, the bottom plate is connected to V in and the top plate is connected to VCM. The main reason for area reduction is now sizes of the maximum capacitor is limited to 4C. Even though we have two of them, which makes it 8C, still is much less than 2 to the power 6C. And one more thing is, because capacitor values are reduced, naturally energy consumption will reduce. So this is relatively obvious reason for energy and area reduction in this configuration. And the division is performed by using 8x7C capacitor, which is connected to the left side, which is LSB-RN, and right side. So in the next slides, I just show you some simple example of how division is happening. And we don't spend more time on this architecture because it is a well-known architecture, only switching scheme and the way voltage levels are defined are different, and I wanted to show you. So same thing that we expect to happen in the traditional binary weighted division, here also is happening by making this 8x7C capacitor to be series with the total capacitor at the MSB array side or LSB array side. So here we are talking about the LSB array operation. Therefore, MSB array is 7C total capacitor and switching is happening here. And for simplicity, I am just showing you the switching from 0 to V full scale because the main motivation is to show the division. Total value of capacitor shown in this square is 7C plus 56/57C. And if we simplify it, eventually Vy, which is on the left side of the capacitor C, will be a capacitive division between C and 455/57C. And then the value of Vx itself becomes a division between Vy from Vy with respect to capacitors of 8x7C and 7C. So Vy itself is 57/512 V full scale, and therefore Vx becomes 8/512 Vy, which reduces to V full scale by 2 to the power 6, which is LSB value reference corresponding to LSB values. Similarly, if we have the switching at the MSB side, MSB array side, similar division is happening. So here LSB side is 8C, total capacitance at the LSB side is 8C, and the equivalent capacitance becomes C. So therefore, the capacitive division will give us Vx, which is a division based on C and 7C. And therefore, we will get the equivalent division for the LSB, for the MSB, which is V full scale by 8. So moving towards recent techniques which are reported for the high efficiency capacitive switching, I want to show you how different switching schemes can change the energy consumption in the capacitive switching. And that's the main focus of this paper based on the example of pie charts we notice in the beginning of this lecture. Let's start with the two capacitive switching in opposite polarity, which is very common in the traditional switching scheme of capacitive DAC. So here the example is shown when we are at time t and moving to the next cycle, which is time 2t, and 3 bits, simply 3 bits are shown over here, and we are going with two capacitor switching. Again here for simplicity, I am showing you V full scale and 0. So how much energy is consumed? Because capacitor C1 has bottom plate connected to ground, which will be later on connected to V full scale, therefore polarity of charge across C1 has to change. Similarly for C2, because the top plate of C2 is connected to V full scale, but later on it has to be connected to ground, therefore polarity of charge across C2 also is changing. And when we have two capacitor switching, so we are eventually changing the polarity of charge on two capacitors. So we expect to have relatively high energy drawn from V full scale, and that is happening. So therefore, as we move from V full scale by 2 reference level, which corresponds to time t, to reference level of 1/4 V full scale, which corresponds to time 2t, we have the energy consumption of 5/4 C0 V full scale square. Derivation of the energy consumption was explained in the previous module of this series of lectures. So this energy consumption is not optimal and can be reduced. So it is interesting to see how we can reduce this energy consumption. This is traditional standard switching till now. So the first thought around this is, why not to look at two-step switching? In fact, this is based on the paper reported in ISCAS 2005, IEEE ISCAS 2005, and interested audience may refer to this paper, which is reported by Ginsberg. So if we don't go suddenly with single step two capacitor switching, if we go step by step, we will be able to save energy. The reason is because we reduce first the voltage across the capacitor, for which the voltage has to go down finally, and therefore the energy loss will reduce. So this is shown here. We introduce an intermediate step that is called time 1.5t. So, and that is the way we generate a two-step switching instead of one step. So instead of switching C1 and C2 at the same time, first we switch C1 without changing C2. So now what will happen is, this is corresponding to increasing Vx. You may ask, why are we doing that? Because this is for moving from 1/2 V full scale to 1/4 V full scale. But the key point here is, if we increase the value of capacitor first, which naturally increases the effective V full reference level, which is 3/4 V full scale now, it helps us to reduce the voltage drop across C2, and therefore the further energy loss reduces. So now if we calculate the energy transition, it will have two energy consumption steps. One will be when we go from T to 1.5T, and one when we go from 1.5T to 2T, in contrast to the standard traditional technique. So if we go from T to 1.5T, the total energy consumption is C0 V full scale square by 4, because here we are actually increasing the voltage, and the overall energy consumption is low, because we are just changing the polarity across C1 and we are reducing the voltage across C2. So therefore, in the next step, when we move from 1.5T to 2T cycle, we notice that only C2 is switching with a lower voltage across it. And therefore, the energy consumption now is C0 V full scale by 2. So, total energy consumption becomes 3 by 4 C0 V full scale by V full scale square as compared to 5 by 4 C0 V full scale square for the traditional technique. Now, keep this in mind. So, what we did? We moved from V full scale by 2 to intermediate 3 by 4 V full scale, and then we reached to the final target value of 1/4 V full scale in two-step switching. But this is not the only way. We can think of other ways as well. Next step is, we go step with two-step switching, but we do one more thing. We disconnect V full scale from the capacitors at time equal to 1.5T, because anyway, at 1.5T, no comparison will be performed by the comparator. So, therefore, we are not so concerned about the value of Vx. So, this helps a lot, because when we disconnect at time equal to 1.5T, the V full scale from capacitors effectively, other than this slight power which is happening because of the non-ideal effects during switching, we don't draw energy from V full scale. Therefore, the transition from T to 1.5T is eventually ideally of 0 energy loss. What will happen for the voltage? Because now we will have charge redistribution across C1 and C2, which are connected in series now. Voltage across Vx will not change, because the current loops only in the loop formed by C1 and C2. So, therefore, the Vx will remain same as before. So, Vx of 1.5T is same as Vx of T. But Vc value, which is eventually the top voltage, which was V full scale, now changes to 2/3 of V full scale because of charge redistribution between C1 and C2. So, now we move from 2/3 of V full scale to the next step, which is 1/4 of V full scale, which is the target value. So, if we consider common denominator, multiple is 12. So, 2 by 3 will be eventually 8 by 12, and 1 by 4 is 3 by 12. So, we are going from higher to lower, and this is 6 by 12. So, still we are going from lower to higher, back to lower, but energy consumption even is less than the previous case when we went with two-step switching. This is also two-step switching plus disconnection of V full scale from top capacitors. So, here when we move from 1.5T to 2T, we have only charge variation across C1, which determines the energy drawn from V full scale, and that reduces to 7 by 12 C0 V full scale square, and the total energy naturally becomes 7 by 12 C0 V full scale square, which is less than the previous case, which was two-step switching without disconnecting V full scale. So, these are two interesting examples. Moving on to the next step is, why not to actually split DAC itself? In the sense that we have a capacitor C2, which is 2C0. Why not to split it into two capacitors? They are parallel capacitors anyway, but do the switchings for these two capacitors separately rather than considering both of them are a part of C2. That's why C2 here is shown as parallel combination of C2-1 and C2-0. Value of both of them is same as C0. They are equal. Now, we are still going with the same example of two-cap switching, but here what we do simply is, instead of going with switching C2 to ground and C1 to V full scale, we simply switch one part of C2 to ground, which gives us exactly the same configuration we expected. by having two-step switching and having two-cap switching. So here, interesting point is we have single-step switching, but with a splitted DAC. So one capacitor, which is C21, now is connected to ground, and therefore energy consumption reduces to 1/4 C0 V full scale square. And directly we reach from 1.2 V full, 1/2 V full scale to 1/4 V full scale, which was the target reference value. So these are three interesting examples to learn how we can use different switching schemes for capacitive DAC to reduce the energy consumption of capacitive DAC, which contributes significantly to the total energy consumption of SAR ADC. And this is important for low energy, medium towards high resolution SAR ADCs. So conclusion here is, we reviewed eventually split capacitor array DAC, which is a well-known, relatively old technique, as a method which reduces both power and area. With respect to binary cap switching, we learned three different methods of switching as compared to the standard switching, which helps us to reduce the extra energy which is consumed from V full scale due to the switching of opposite polarity capacitors. So we reach to the end of this lecture. Wish you all the best.